So hi everyone, welcome back to another video. Today in this video, we are going to do bit manipulation rapid revision. Since placement season is coming soon, so either there is interview or online assessment, revising any DSA topic and its important patterns is very difficult. But don't worry, because in this video, we are going to first do the introduction of bit manipulation and its basic bit operations very quickly. Then we will jump to the 5 important patterns that I found really helpful while solving the questions on platforms like Codeforces, CodeChef and Leetcode and even interviews as well. Also, with every pattern, we will going to discuss that where this pattern, in which question this pattern can be applied. Also at the last, I will be giving you a challenge for which the solution you will be adding in the comments. So before starting the video, I would request everyone to please like, share and subscribe to my channel and also share this video to your friends and also do tag me wherever you can. It will motivate me for bringing more such content. So let's get started. So let's start with the introduction of bit manipulation first. So bit manipulation generally has binary numbers that have 2 digits, either 0 and 1. So for example, 1011 is a binary number. Why? Bi means 2, that means 0 and 1. They are 2 digits and binary number is represented in either 0 and 1. So 1011 is a binary number, right? So if we want to convert the binary number to a decimal number, then we will do it like this. So let me tell you in simple words, decimal number has 10 digits, right? And it has 0 to 9 digits which are involved. That's why it has 10 digits. It is similar to binary numbers that have 2 digits and they have either 0 and 1. So if we did the expanded form, let's say 2463, it can be written as 2 into 10 raised to power 3 plus 4 into 10 raised to power 2 plus 6 into 10 raised to power 1 plus 3 into 10 raised to power 0. This is the expanded form of the decimal number. So if I want to convert this binary number to a decimal number, it will be similarly done like this. So what we will do, since binary number has 2 digits, so we will say multiply it with 2 raised to power 0, it with 2 raised to power 1, it with 2 raised to power 2, it with 2 raised to power 3 and add all of them to get the decimal number. So this is the binary number and this is how we will convert the binary number to the decimal number. Now let's discuss the basic bit operations very quickly. So we have bit operations like AND, OR, NOT, XOR, left shift, right shift. So let's discuss each bit operation. AND operation is represented by this symbol, and AND operation says that if we have 2 bits, let's say 1 and 0, if at least one of them is 0, we will always get 0. Like for example 0, at least one of them 0, we will get 0. Here both of them is 1, we will get 1. Here at least one of them 0, we will get 0. So for example, if I give you a number in the binary form, let's say 101 and 011. So if I do AND of them, so 1 and 1 is 1, 0 and 1 is 0, because at least one of them is 0, we will get the 0. So let's jump to the next bit operation, that is the OR operation. OR operation is represented by this symbol. It says that if at least one of the bit is 1, we will get 1. So 1 or 0 is 1. 0 or 0 is 0. 1 or 1 is 1. So you can see, like, if at least one of them is 1, we will get 1. Similar to this example, 101, 011, we will get 1, we will get 1, we will get 1. But if both of them is 0, we will get 0 because no one is 1 here. Let's jump to the next bit operation, NOT operation. NOT operation is represented by this symbol. So it says that if I do NOT of 1, we will get 0, and if I do NOT of 0, we will get 1. So it's similar to the opposite. 1's opposite is 0, 0's opposite is 1. So if I give you the example, 101 NOT is 010, like just opposite. Let's jump to the next bit operation, that is XOR operation. XOR operation is represented by this symbol. And it says that if 2 bits are same, we will get 0, otherwise we will get 1. So for example, if I say 1 XOR 1 is 0, 0 XOR 0 is 0, but 1 XOR 0 is 1, 0 XOR 1 is 1, because one of them is 1, we will get 1, otherwise if both are same, then we will get 0. So if I give you the example, 101, 011 XOR is 11 is 0, 01 is 1, 10 is 1, right? Let's jump to the next bit operation, that is left shift operation. Left shift operation is represented by this symbol. It says that if we have number in the binary form 10111 and we do left shift of 2, then 10 will be removed and 2 zeros will be appended at the end. But it is actually wrong. Generally, integer has 32 bits. So if I say here from 0 to 32 bits here, that is in the 0 base indexing, it will be 31st, right? Now, if we have 1, 0, 111 here, then ahead of them we'll have 0. So if I do left shift of 2, then ahead 2 zeros will be removed and 2 zeros will be appended at the end. So actually 1 and 0 will not be removed. Rather, zeros ahead will be removed, right? Now, this is a one thing that you need to know. Let's jump to the next bit operation, that is right shift operation. Right shift operation is represented by this symbol. It says that, for example, if we have number 10111 in the binary form, and if we want to right shift 2, so what we will do, we will say like 10111, two ones will be removed from the end. Why? Because it is shifted by 2 positions and extra zeros will be appended at the beginning. So we have again skipped the zeros for understanding, but I think you got the point that last 2 bits will be removed and ahead 2 zeros will be appended. So these are all the basic bit operations. And one more thing that I want to clear to you, that what is most significant bit and what is least significant bit. Most significant bit is latest bit, that is 31st bit is the most significant bit, and 0th bit is the least significant bit in the integer numbers. Let's jump to the core part of this video, that is 5 important patterns, or you can say tricks, that are really helpful while solving the problems. So let's discuss the first trick, that is zero Xorsum property. Zero Xorsum property is like, I have given random name, you can give it any name. So it's just the name that I've given according to its use case. So zero Xorsum property says that, as we have discussed in the Xor, that if 2 bits are same, for example 1 Xor 1 is 0, 0 Xor 0 is 0, right? So it means if I have 2 numbers, if I represent them in the form of binary form 101, then if I Xor, we will get 0 obviously. Why? Because both bits are same always, right? So from this I can say if n Xor n is 0, right? And also n Xor 0 is n. Because anything that I do Xor with 0, we will always get the n only, right? So from this, let's understand that point, that if we are doing Xor till 4, from 1 to 4, 1, 2, 3, 4, and we are again doing Xor of 1, 2, 3, 4, and we are doing both Xors, it means, for example, if I say x is 1, 2, 3, 4 Xor, and y is 1, 2, 3, 4 Xor, and if I say x Xor y, then what will I get? 0. Why? Because it's pretty obvious what we are going to do. 1 Xor 1 is 0, 2 Xor 2 is 0, 3 Xor 3 is 0, 4 Xor 4 is 0. Now how this trick will be useful? So this trick is really useful while solving the questions like missing element and repeating element. For example, if I tell you we have the numbers from 1 to 4, 1, 2, 3, 4, and if I tell you an array, I have an array where numbers are 1, 2 and 4. So I am asking you that find out the missing number. You know that is 3, but actually in terms of code, how can you do that? Then what you will do, you will do Xor of all of them. You will get the missing element. How? Because 1 Xor 1 is 0, 2 Xor 2 is 0, 4 Xor 4 is 0. So remaining 0 Xor 3 is 3, right? So from this we can understand that whenever you are doing same number Xor, you will get 0. So since 3 is left, so you will get the final element 3. Similarly, this trick can be applied in repeating element as well. So you can find out the repeating element easily. Let's jump to the next trick, n and n minus 1 bitwise trick. So why I have given it name as n and n minus 1? This is because using this, we are going to find various patterns. So let's start. So first pattern is n and n minus 1 0. It can only happen when n is a power of 2. Let me explain it. So if I tell you 2 is 1 0, 4 is 1 0 0, 8 is 1 0 0, 16 is 1 4 times 0, right? This is one thing. So that means any power of 2 can be represented by 1 bit only. For example, if I say 8, 1 0 0, because it's obvious that every binary number can be represented in 2's powers only, right? So this is one thing that is clear to us. Second thing is why for every power of 2, that is, for example, it is 2 raised to power x, its previous number is just opposite in the binary form. For example, 4 is 1 0 0, then 3 is 0 1 1. Why it's just opposite always? For example, if I say, let me ask you one thing. If we have 2 bits and I ask you find out all the permutation combination of these 2 bits using the binary number. So you will say, we can say 0 0, 0 1, 1 0 1 1. So you can see only these 4 permutation combination I can create, and these 4 numbers I can only create now. So I will say, if I ask you let me start the new number, so what you will say? I will start with 1 0 0. So you can see you are again starting with a new bit. So that means you are just making the opposite only. You can also compare, for example, if I say 1 1 1 last number, and if you want to start with new number, then you will say 1 000. This is because all bits are finished now. All permutation combination are created now. So we need to start with new number. So take new bit and start now. So that's why whenever n is a power of 2, n minus 1 is opposite in the binary form. So we will say that whenever n is a power of 2, n and n minus 1 is equal to 0. Otherwise it will not be 0. So this thing can help us to easily identify that n is a power of 2 or not, right? So here I have already tell you, if I give you n minus 1 and if I do plus 1, that is n. So it's just inverting the bits only, nothing more than that. Let's start with the second pattern that is interrelated to the above one only, remove rightmost set bit. So if I tell you that, so let's say n is 1001 1000, then what will be n minus 1? So n minus 1 will be, let's find the rightmost set bit first, 1. Just invert this part only and remaining part will be remain as it is. Explanation will be interrelated to above one only. If I have 0 1 1 and if I ask you give me next number, then what you will say? All permutation combination are finished. 1 1 1 is the last number in the binary form. The next number will start refresh with the 1 000 only. So again, since the ahead part remain as it is and the previous number, since all permutation combination are finished, we will start refresh with new number. So that's why we are getting the opposite from the rightmost set bit only. The head part will not be changed, right? So now this thing is done. Then what is remove rightmost set bit? So if I say you do n and n minus 1, then what you will say? That we are taking rightmost set bit and reverting only this part. That means if I do and, this part will remain as it is and rightmost set bit will be removed. So from this we can understand whenever we want to remove rightmost set bit, do n and n minus 1. What it will be do? It will take rightmost set bit and inverts it all part, ahead part will remain unchanged. Now using n and n minus 1, we found that we can remove rightmost set bit. But what if I say don't remove rightmost set bit, give me rightmost set bit? For example, if I say 1001 1000 in binary form, if I want to remove rightmost set bit, you will say remove it, you will get 0, right? This is like that. Now if I want to tell you that give me this rightmost set bit and make all of them 0, then what you will say? Do n and not of n minus 1. Why? For example, n is 1001 1000, right? N minus 1 will be 1001, opposite of rightmost set bit 0111, right? Now if I say do the not of n minus 1, then what it will be? This part will be reversed 0110 and this part will also be reversed 1000. So what will happen? For this part is opposite now, so it will always give us 0, right? And for this part will remain same. Why? Because this part was reversed and again this was reversed, so we get same number. 100 opposite is 011, 011 opposite is 100, so we got actually same number only. So we will say that for getting the rightmost set bit, do n and not of n minus 1. For removing the rightmost set bit, do n and n minus 1. Now there can be another trick that you can find. Count set bits of number. So there is an algorithm called Brian-Kernighan's algorithm. I don't know how to pronounce this name, but this algorithm says that using this n and n minus 1, you can easily count the number of set bits. Like how? As I already told, n and n minus 1, what it will do? It will remove the rightmost set bit. For example, if I tell you 1011, n and n minus 1 will remove rightmost set bit, it will become 0 now. Again, n and n minus 1 will remove rightmost set bit, it will become 100 now. Again, n and n minus 1 will remove the rightmost set bit, it will become 000 now. So finally we got the 0. So it says that this algorithm is interrelated to the explanation we have studied above, that do n and n minus 1 until you get n is equal to 0. So do the count plus plus, because in every step you are removing the rightmost set bit only. So in actual, The number of step is number of set bits only. So this is the Bryan-Kernighan's algorithm. So this was about this trick that we have used. So this is a very important trick, and you can see from this trick we found various patterns now. So let's jump to the next trick now. Let's discuss the next trick, Xor of ranges 1 to n. So if I ask you, find me the Xor till n, from 1 to n, then how will you do that? Then you will say like, let's run a for loop from 1 to n and find out the Xor. So it's actually big O of n time complexity. But if I tell you, I have a way to find out in big O of 1. So let's see that way. Actually, I found this way while giving a code forces contest. So let's discuss. So we are going to get the follow-up understanding. Then we will be getting intuition like why this general formula is always applying. Let's see. So if I ask you that Xor till 3 is 0. So 0 Xor 4 is 4. We have already discussed like n Xor 0 is n. You need to assume that Xor till 3 is 0, right? I am saying that in the group of 4 numbers, every third number, till the every third number we will be getting 0. So if I do 0 Xor 4, we will get 4. If I do 0 Xor 8, we will get 8, right? So this is clear. If n modulo 4 is 0, we will get n. We are assuming that previous number will always give us 0. So let's discuss the third number. Why it will always giving us 0? So let's again assume that the previous number will always give the same number. For example, if I say 1, 2, 3, then previous number will give us 3. Okay, so 3 Xor 3 will be 0, right? Again, if I tell you Xor till 6 is 7, so 7 Xor 7 is 0. We are assuming that previous Xor will be equal to the number. So if I are assuming that previous Xor will be equal to the number, then n modulo 4 is equal to 3. Whenever n modulo 4 is equal to 3, that is third element of each group, will always give us 0, right? But we are assuming that second number of every group will always give us the same number. Now let's discuss. Now 1 Xor 2 is 3. How? This is because 2 is 1 0, 1 is 0 1. So if I do Xor, 1 Xor 0 is 1, 0 Xor 1 is 1, we will get 3. Now let's say I tell you that again in the second group, this will give us 1. Right? I am saying you that first number of every group is giving us 1. So what will be the next number? Since we know that this is 2, 6, 10, 14, every number will be the even number. Second number of every group will be the even number, right? So every even number, for example, this is 1. We are saying that first element of every group is 1. So 1 is 0, 1. 6 is the even number. We know that this is even number. So 1, 1, 0. So when we do the Xor, we will get 1, 1 same as it is, but we will get extra 1. So it is like we are doing n plus 1 only. This pattern will repeat again and again for every second number. So we will say if n modulo 4 is 2, we will get n plus 1. But we are again assuming that every first number of each group is 1, right? Now we were assuming that every first number was 1, right? So how it is? Like 1 is 1 always, right? This is 4. 4 Xor 5 is 1. Why? Because if I tell you that 4 is 1 0 0, 5 is just plus 1, 1 0 1. So when I do the Xor, these number will be cancelled, these bits will be cancelled, and remaining 1 is 1 only. So we will always get 1. So let me tell you, let's say 8. 8 is 1 0 0. Next number is 1 0 0 1. Next number is always odd number, right? So odd number has only one thing, that last one bit always be added. So like, let me tell you one more thing, that I create any binary number. So if I add 1 at the end, then it will become odd. Otherwise it will never be odd. Why? Because in the binary number, last number is the only one number that is the odd number. Otherwise all numbers are in the power of 2 and they are even only, right? So this is 8, 1 0 0, and if I add 1, it will become 0 0 0 1. So we can say that every group has a last number. It will always be even. Fourth number will always be even. Next number is just plus 1. So that is the odd. So odd number has extra 1 at the end. So when I do the Xor, all ahead bits will be cancelled and the last bit will be taken. So we will always get the 1. So this trick is very, very useful whenever you want to find Xor sum till n in big O of 1 only, right? So now you will ask, like, should I remember this trick for always? Like whenever any contest comes, I need to solve the question very, very quickly. Then how will I? Should I derive it? No. Just take this 4 elements of the first group and just derive it from there. Like n modulo 4 is 1 1. This is 1 XOR 2 is 3, that is n plus 1. 1 XOR 2 XOR 3 is 0, that is always 0. And this is 4, till the 4 answer is 4, that is n. So from this just you can derive, but if you are asked this in interview, then you need to explain this reason. So just understand, but in the context you can just easily derive it and just use it, right? So now in big O of 1 we can find the Xorsum, right? Let's jump to the next trick, that is count set bits from 1 to n. Now, if I ask you that count the set bits from 1 to n, then what you will do? You will run a for loop till n, and for every number you will run a loop for 32 bits. For each integer has 32 bits, so you will run a 32 bits for loop and you will count the number of set bits. So that is a complex is big of n into 32. But generally when we solve the questions on Leetcode or any contest, we have the tight constraint and we need to find it in very less complexity so that we can solve other part of code as well, right? So if I tell you there is a way which can find the set bits, count the set bits in login technique only. So let's understand that. This trick needs your more attention. So let's understand it clearly. So if I ask you, we need to count the set bits till 13. Then what we need to do? We need to just understand the first method. Then we will get intuition like how it is working, right? Now if I ask you count set bits till 13. So I will say for 13, find out the latest power of set bit. So you will say that 13's latest power of 2 is 8. Right, not 16, 8. I want smaller one. So latest power of 2 is 8, right? So you will say, write down all the numbers from 0 to 7. That is before 8. We have written these numbers. Now, 8 is 2 raised to power 3. What it is actually? We have 3 bits. 2 raised to power 3 represent, we have 3 bits. And every point has 2 numbers. 0 and 1, 0 and 1, 0 and 1. So here we can see, we are just getting all the permutation combination of these 3 bits, right? So like 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0 like these, right? So one thing is clear also that at every point we have 4 bits, 4 set bits. Again here 4 set bits, 1, 1, 1, 1, 1, 1, 1, 1 like. So why this is happening? This is because since we have 8 numbers that are created from this permutation combination, so 4 zeros will be there and 4 ones will be there, 4 zeros will be there, 4 ones will be there. Again same. So we will say finding the latest power of 2, for 13 it will be 3, highest power of 2 will be 3 here, right? So we will say that 2 raised to power 3 minus 1 is 2 raised to power 2 because 4 are there, 2 raised to power 2 is 4. So we'll say 2 raised to power HP minus 1, highest power minus 1 into how many times? 3 times. That will give us the total number of set bits till 8, before 8, right? So we got the total number of set bits before 8 very easily. Just by taking a small formula, we got the total number of set bits. Now, how to find these set bits now? Now what we will say, we know that these numbers are there. We will say count the set bits from here first. So what are the number of set bits? So it is 8, 9, 10, 11, 12, 13. So 13 minus 8 is 5. 5 plus 1 is 6. So we have 6 set bits here. So we will say n minus 2 raised to power HP plus 1. That is whatever is the number minus 8 plus 1 will be the number of set bits here. So remaining part is this now. What it is actually? It is actually the same thing that we are doing firstly. 0, 1, 2, 3, 4 and again find outing the latest power of 2. So what we are actually doing? Doing the same thing. And while doing the same thing, what we do? Recursion. N minus 2 raised to power HP. Why not plus 1? This is because it starts from 0. 0, 1, 2, 3, 4, 5. And it was actually 6 ones. But actually it was 0, 1, 2, 3, 4, 5. That's why number is 5. But number of set bits are 6 at the beginning. So we will say n minus 2 raised to power HP. So we call this recursion. So again the same thing applies inside. So this is actually the login method. So here you can see first we find the latest power of 2. That is highest power is log to n. That is 3. Then we will using just some observation we got this formula, right? And after that we take these set bits, extract out these set bits and remaining is this number. And this number is the recursion. We will call the recursion for this and we will get the other data for this, but recursion will handle this. Similarly, it will call this for 5, latest power of 2 is 4. Till 4 I will apply this formula. Then I will again count the set bits. Then I will call the recursion, and like that it goes and goes. So in the log n complexity only you got the count of set bits from 1 to n. That's a very good thing, and that's a very good optimization you can use in your any question, right? So this was about this trick. Let's jump to the next trick, that is DP with bitmasking. I found this trick very helpful while solving the Leetcode hard question. Bitmasking is just a looking like difficult word, but it's not actually. So if you don't know DP, don't worry, because I will be telling you in short like how DP works, and then I will jump to this bitmasking thing, right? So DP is like it avoids the overlapping subproblems. For example, I will give you just a simple recursion function f5. If I say find out the Fibonacci of fifth number, so you will say I will call the fn is equal to fn minus 1 plus fn minus 2, right? So f4 of f3, then f3 of f2, then f3 says f2 and f1. So here what you can see for f2 we are finding again and again, but obviously result of f2 will always remain same, right? If Fibonacci of 2 is 1, then it will always remain 1. It will obviously not change. So why we are repeating this thing? So that's the DP optimize. It says avoid overlapping subproblem by storing the state. So instead of recalculating this 2, store it somewhere in the array so that I can reuse it again. So this is the DP, right? So in short, I have talked about DP. Now generally DP array is a multi-dimensional array, not only single dimensional array. For example, if I tell you we have a function of I comma j, and these two elements are just varying, like for example, if I say in between it calls fi of j plus 1, fi of j minus 1, fi plus 1 comma j. So here you can see these two elements will always change. So whatever elements change, those elements are added in the dimensions in the DP, right? Whatever is the highest power, highest limit of all these dimensions, whenever we multiply the highest limit of all these dimensions, and whatever we get, this is the time complexity. Let's say if I have requirement to make a visited array. So you will say, how can I store a visited array in this dimension only? So obviously there comes the bit masking. So you, in simple words, you can say bit manipulation. So what is visited array? So you have solved many backtracking and recursion question. There you can see we maintain a visited array, that at this point queen was there or not, or something, right? So true, true, false, false. Let's say this is a visited array, and let's say in this visited array DP of 2, 3 is 4, right? And let's say for this visited array true, true, false, true, DP of 2, 3 is 5. Why this changes? I already said what DP stores. DP stores a changing part. Since visited array is also changing, so this should also be added in the dimension, otherwise we will get different answer, right? If it was 2 and if it was 3, then it was fine, but DP of 2, 3, DP of 2, 3 can't be different. Why they are different? This is because visited array is also changing, and this should also be added in dimension. Here bit manipulation helps. Bit manipulation says that instead of storing the visited array, let's store the number. That number in the binary form will represent as visited array. So let's say I give you a number, let's say have 4 bits. It initially has 0. And if I say let's make it 1, then what will happen? That means first element is visited. It's similar to false, false, true, false, right? It is similar to visited array only. But it's actually a number in the decimal form. So in the decimal form, what it will be? 2 raised to power 0, 2 raised to power 1, that is 2. This is the 2. So we can say that if we want to represent the visited array, but we want to store it in DP, then how we can do that? We can simply create a number of 0, 0, 0, 0, and whenever we want to mark any number as visited, what we will say, just mark it bit as visited. That means we got the 0, 1, 0, 0, that is 4, but this 4 internally representing the visited array. So DP of xy 16. So this 16 is the dimension which we have added for maintaining the visited array. So time complexity will be x into y into 16. So we can say if we want to store true, true, false, false in the DP. So we will say DP of xy, another dimension in the binary form is 1, 1, 0, 0, but it's actually a decimal number only 4 plus 8, 12, and this is actually this 11. So dp of xy of 12 is representing some value 4, dp of xy of 11 is representing some value, let's say 5. So I hope you got this, but it's actually somehow difficult if you don't know the dp. This pattern is really useful while solving the Leetcode hard question many times, because I personally found it really useful while solving the questions. So these are the 5 important patterns, or you can say tricks, that are really helpful when I solve the questions on Leetcode, CodeFreeze and CodeChef, and even interviews as well. These are the important tricks. So whenever you want to give the explanation, now it will be easy to give, because I have given the in-depth explanation for each pattern. So now the times to give you a challenge. So the challenge is swap two numbers using bitwise operations, and don't use swap A and B. Use a bitwise operator to swap the two numbers. Let's see the solution in comment. Also, do comment out if you want more such videos. So this was all about video. If you like the video, please like, share and subscribe to my channel for keep motivating me for bringing more such content. Thank you and have a nice day.